When a star dies, it doesn't vanish, it collapses to its limits, transforming into a neutron star. Their internal laws are unlike anything known to physics. Albert Einstein. In the vast, dark expanses of our universe, where distances are measured in light years stretching into unimaginable reaches, lies one of the most magnificent phenomena known to modern science: neutron stars. These celestial bodies, remnants of massive stars that have undergone catastrophic supernova explosions, are both a captivating spectacle and a source of genuine awe due to their immense power. They represent the greatest paradox of the cosmos: incredibly dense yet miniature, born of death yet sources of unimaginable energy. But how exactly do they come into being, and what is the terrifying power that these stars possess? Neutron stars deservedly rank among the most astonishing and powerful objects in the universe. Their story begins with the life cycle of massive stars, many times larger than our Sun. As these giants approach the end of their existence, they conclude it with a resounding bang, a spectacular explosion known as a supernova. This dramatic event becomes the cradle for neutron stars, marking the transformation of a dying star into something extraordinary and mysterious. For millions of years, a massive star burns nuclear fuel in its core, generating energy that resists the force of gravity, which seeks to compress matter inward. This delicate balance maintains the star's stability for most of its life. However, when the fuel supply is exhausted, this equilibrium is disrupted. Without the outward pressure sustained by nuclear fusion, gravity takes over, causing the star's core to collapse. The star's outer layers are then ejected into space in a supernova explosion, one of the most powerful events in the universe. As the star's core collapses, it undergoes phenomenal changes. The colossal gravitational force compresses the atoms of the core, forcing protons and electrons to combine and form neutrons. The result is a dense ball composed of neutrons, a neutron star. Despite having a mass twice that of our Sun, a neutron star is incredibly small, typically only about 20 kilometers in diameter. To put this into perspective, it's comparable to compressing the mass of an entire mountain into a space the size of a city. This collapse leads to the formation of an object with astonishing density. Just 1 teaspoon of neutron star material would weigh billions of tons on Earth. The gravity on the surface of a neutron star is also incredibly strong, approximately 1 billion times stronger than on Earth. This means that if someone could stand on the surface of a neutron star, which is, of course, impossible as they would be instantly crushed, their weight would increase a billionfold compared to their weight on Earth. The existence of neutron stars was first hypothesized in the 1930s by Swiss astronomer Fritz Zwicky and German-American astronomer Walter Bode, working at the California Institute of Technology. They suggested that supernova explosions could lead to the formation of stars composed primarily of neutrons. At the time, this was a bold and groundbreaking idea, as the concept of such dense objects was difficult to imagine. The pioneering work of Zwicky and Bode laid the foundation for future research and observations that eventually confirmed the reality of neutron stars. Studying neutron stars is a challenging task due to their small size and immense distance from Earth. Nevertheless, advancements in technology have allowed astronomers to observe these enigmatic objects and gain new insights into their nature. Modern observations rely on a variety of methods and telescopes, each providing unique information about the properties of neutron stars. One of the most crucial tools for studying neutron stars is the X-ray telescope. Neutron stars are often detected by the intense X-ray radiation they emit, especially when they are part of a binary system. In such systems, a neutron star can pull matter from its companion star, heating it to extreme temperatures and causing it to emit X-rays. The Chandra X-ray Observatory and the XMM Newton telescope are among the leading instruments used to observe these high-energy phenomena. The study of neutron stars relies on diverse methods, allowing scientists to peer into the mysteries of these exotic celestial bodies. One important technique involves using radio telescopes to detect pulsars, a type of neutron star that emits regular pulses of radio waves. These cosmic beacons, as they rotate, sweep beams of radiation from their magnetic poles across the sky. Thanks to the precision of these pulses, astronomers can study the rotation and other characteristics of neutron stars in detail. The Arecibo Observatory, before its destruction in 2020, and the Parkes Observatory in Australia have made invaluable contributions to pulsar research. In recent years, gravitational wave detectors like LIGO and Virgo have ushered in a new era in the study of neutron stars. Collisions between two neutron stars generate ripples in space-time known as gravitational waves. These cosmic cataclysms are not only a spectacular sight, but also a treasure trove of information about the properties of neutron stars. In 2017, the merger of neutron stars was detected, marking a significant milestone in astronomy, allowing scientists to observe this event simultaneously in gravitational waves and electromagnetic radiation. A neutron star is a striking cosmic object composed of several layers, each with unique characteristics. At the very center of the star is the core, its densest part. The core is surrounded by a crust which, though less dense, is still incredibly compact compared to any matter known on Earth. Above the crust lies a thin atmosphere, a rarefied layer that interacts with the surrounding cosmic space. The core of a neutron star is where truly astonishing phenomena occur. It is almost entirely composed of neutrons, subatomic particles that make up the nucleus of atoms. Under the colossal pressure of gravity, these neutrons are compressed to such an extent that it defies our conventional understanding of matter. The density of the core is so immense that 1 cubic centimeter of this substance would weigh hundreds of millions of tons on Earth. Surrounding the core is the crust, which also possesses incredible density, though it is less dense than the core. The crust consists of ions and electrons, but with increasing depth, the density increases and atoms break down into neutrons. This layer, only a few kilometers thick, plays a crucial role in the star's structure and behavior. It is within the crust that the neutron star's magnetic field is generated, one of the most powerful in the universe, exceeding Earth's magnetic field by 1 trillion times. Above the crust lies the atmosphere, a thin layer only a few centimeters thick. This atmosphere, composed primarily of hydrogen and helium, is where the star interacts with its environment. The atmosphere's temperature can reach millions of degrees, and it emits X-rays and other types of radiation that are detected by terrestrial telescopes. The forces that prevent a neutron star from collapsing under its own gravity are truly astonishing and originate from quantum mechanics. One key factor is the pressure of degenerate neutron gas. In ordinary stars, nuclear fusion reactions create pressure that prevents collapse, but in neutron stars, the situation is different. Here, quantum mechanics comes into play. The Pauli exclusion principle, a fundamental law of quantum physics, states that no two neutrons can occupy the same quantum state in the same space. This principle creates a pressure that counteracts gravity, the degenerate neutron gas pressure. It is this pressure that supports the star and prevents it from turning into a black hole. Neutron stars possess incredible density, and the gravity on their surface is so strong that if any object were to fall from a height of 1 meter, it would reach the surface in fractions of a millisecond, accelerating to a speed of over 1,000 kilometers per second. To visualize the density of a neutron star, imagine a piece of its material the size of a sugar cube. This tiny fragment would weigh about 1 billion tons, comparable to the weight of the entire human population of Earth. Comparing the gravitational pull on the surface of a neutron star to that on Earth is almost impossible. On our planet, a person jumps and gently descends back down. On a neutron star, gravity is so immense that any body would be crushed almost instantly. Even photons of light struggle to overcome the gravitational field of such an object. Because of this, neutron stars can bend light around them, creating a gravitational lensing effect. The extreme conditions within a neutron star create a unique environment where nuclear reactions and quantum effects reach scales and intensities not observed anywhere else in the universe. The core of a neutron star has colossal density, with neutrons packed tightly together. This state of matter, called neutronium, is extremely rare and can only exist under the most extreme conditions. The outer crust of a neutron star is also an amazing formation. It consists of a lattice of atomic nuclei immersed in a sea of electrons. As one moves deeper into the star, the density of matter increases and the nuclei draw closer until they dissolve into a peculiar soup of neutrons and protons. In the inner crust, strange and exotic forms of matter may exist, including free neutrons and superfluid components. One of the most intriguing properties of neutron stars are their magnetic fields. These fields can be 1 trillion times stronger than Earth's magnetic field. Such power influences all processes occurring on the star and in its surrounding space. In some cases, the magnetic field is so intense that it can deform the structure of atoms, stretching them into thin filaments. This same magnetic field accelerates particles to nearly the speed of light, creating beams of radiation that we observe as pulsars. Pulsars represent a special type of neutron star that emits regular pulses. This phenomenon is explained by the rapid rotation of the neutron star and the emission of radiation beams from its magnetic poles, which, like lighthouse beams, sweep across cosmic space. When such a beam is directed towards Earth, we detect a pulse. Pulsars are incredibly precise. Some rotate hundreds of times per second, serving as cosmic clocks that allow astronomers to measure time with unprecedented accuracy. Neutron stars are amazing objects on their own, but some of them exceed all expectations due to their magnetic fields. These stars, known as magnetars, possess the most powerful magnetic fields in the universe, exceeding the strength of ordinary neutron stars' magnetic fields by 1,000 times and reaching 1,000,000,000 times the strength of Earth's magnetic field. Magnetars are true magnetic monsters. Their intense magnetic fields influence every aspect of these stars' existence. They are so strong that they can alter the structure of atoms, stretching them into thin, elongated shapes. Magnetic pressure reaches such magnitudes that it can cause fractures in the magnetar's crust, leading to so-called starquakes, analogous to earthquakes but significantly more powerful. These starquakes release colossal amounts of energy in the form of gamma rays. Among the most spectacular and terrifying phenomena associated with magnetars are magnetar flares. These occur when magnetic field lines rupture and reconfigure, releasing an enormous burst of energy. The result is a gamma ray burst, one of the most energetic explosions in the universe. These bursts can be observed from Earth and provide scientists with valuable information about the nature of magnetars. The first recorded magnetar flare occurred on March 5, 1979. Two Soviet spacecraft detected a powerful burst of gamma rays emanating from a distant source. This event, dubbed the March 5th event, was later identified as a flare from a magnetar located in the Large Magellanic Cloud, a nearby galaxy. The burst was so intense that it temporarily blinded the spacecraft's detectors. Since then, numerous magnetar flares have been observed, each enriching our knowledge of these incredible cosmic objects. One of the most renowned magnetar flares is considered to be the event of December 27, 2004. A magnetar, located approximately 50,000 light-years from our planet in the constellation Sagittarius, emitted a gamma-ray burst so powerful that it impacted Earth's atmosphere. This burst was detected by numerous satellites and observatories worldwide. This event vividly demonstrated the incredible energetic force of magnetar flares and their potential impact on Earth, despite the colossal distances involved. Despite the fascination of studying gamma-ray bursts, they pose a potential danger. If such a burst were to occur in close proximity to Earth, the consequences could be catastrophic. Intense gamma radiation could destroy the ozone layer, exposing the planet's surface to harmful ultraviolet radiation from the sun. This, in turn, would lead to a significant increase in skin cancer rates and other health problems for living organisms. Magnetic fields could also disrupt satellites, communication systems, and power grids, causing widespread technological failures. Fortunately, magnetars are relatively rare, and currently, none are close enough to pose a direct threat to Earth. Nevertheless, studying these magnetic giants allows scientists to better understand potential risks and develop strategies to mitigate them. By observing magnetar flares and analyzing their effects, researchers gain valuable insights into how such events could impact our planet. Despite the potential dangers, magnetars hold immense scientific interest. They serve as a unique laboratory for investigating physical processes under extreme conditions. The intense magnetic fields and high-energy environment around magnetars provide insights into the behavior of matter and the fundamental forces governing the universe. By studying magnetars, scientists have the opportunity to test existing physical theories and discover new frontiers in our understanding of the cosmos. Magnetars also play a specific role in the overall picture of the universe. They are interconnected with other astrophysical phenomena, such as supernovae and gamma-ray bursts. A deeper understanding of magnetars allows scientists to learn more about the life cycles of stars, the dynamics of supernova explosions, and the mechanisms underlying gamma-ray bursts. These interconnections make magnetars an important piece of the puzzle in our quest to comprehend the mysteries of the universe. Neutron stars are among the most energetically powerful objects in space. Their energy dynamics are complex and genuinely fascinating. They emit radiation across the entire electromagnetic spectrum, ranging from radio waves to gamma rays. This radiation is a key characteristic of their nature and provides valuable information about their internal processes and surrounding environment. The radiation from neutron stars surpasses most other cosmic phenomena in intensity. Neutron stars possess incredible brightness, especially when observed in the X-ray and gamma-ray ranges. For instance, a single neutron star can outshine an entire galaxy in X-rays. Such high radiation intensity is due to the extreme conditions existing on the star and in its vicinity. Powerful magnetic fields, rapid rotation, and high temperatures all contribute to these energetic emissions. When comparing neutron stars to other cosmic phenomena, it becomes evident that they are true energy giants. While an ordinary star, like our Sun, emits most of its energy as visible light, neutron stars primarily emit energy in the high-energy part of the spectrum. This difference in emission highlights the unique physical processes occurring within neutron stars. A neutron star's luminosity, which is the total amount of energy it emits per second, is closely related to its energy sources. One of the most important energy sources for neutron stars is their rapid rotation. Neutron stars can spin hundreds of times per second, and this rotation generates a colossal amount of energy. As a neutron star rotates, its powerful magnetic field accelerates charged particles to nearly the speed of light, creating directed beams of radiation. These beams can be observed as pulsars, where the rotation causes the beams to sweep across our line of sight, generating regular pulses of radio waves or other types of radiation. In addition to the aforementioned energy sources, neutron stars possess another vital energy reserve, the residual heat generated at their birth. When a massive star ends its life with a core collapse, the resulting neutron star has a colossal temperature. Gradually, this heat dissipates into space, but this process can extend for millions of years. This thermal radiation primarily manifests as X-rays, which modern space telescopes can detect. Analyzing a neutron star's thermal output provides valuable insights into its age and thermal history. Younger stars are generally hotter and emit more X-rays, while older stars cool down and their radiation weakens. The thermal emission from neutron stars plays a crucial role in understanding their structure and behavior. By studying their thermal output, scientists can infer the composition of these stars' crust and core. For example, the cooling rate of a neutron star is directly related to the properties of the superfluid medium in its core and the thermal conductivity of its crust. Observations of thermal emission help refine existing models of neutron star internal structure and offer clues about the existence of exotic states of matter that arise under such extreme conditions. One cannot overlook another intriguing aspect of neutron star energy dynamics, their immensely powerful magnetic fields. As previously mentioned, neutron star magnetic fields are among the strongest in the entire universe. These fields interact with the star's surrounding environment, forming magnetospheres filled with charged particles. The interaction between the magnetic field and these particles generates additional radiation, contributing to the neutron star's overall energy output. Studying these magnetospheres is crucial for forming a complete picture of neutron star energy dynamics. The intense energy emissions from neutron stars have a noticeable impact on their surroundings. For example, a neutron star in a binary system can accrete or pull in matter from its companion star. As this matter falls onto the neutron star's surface, it heats up to extreme temperatures, emitting X-ray radiation. The accretion process is another important energy source for neutron stars and can lead to phenomena such as X-ray binaries and millisecond pulsars. Understanding the energy generation processes in neutron stars is key to unraveling many astrophysical mysteries. These processes are governed by the laws of quantum mechanics and general relativity, providing scientists with a unique laboratory to test fundamental physical theories. The extreme conditions existing within neutron stars push these theories to their limits, offering unique insights that cannot be obtained by studying any other objects in the universe. Neutron stars open a window into an extreme gravitational playground where the very fabric of space-time is warped and distorted beyond recognition. One of the most amazing aspects of these celestial bodies is their role in generating gravitational waves, ripples in space-time predicted by Albert Einstein in his general theory of relativity. Gravitational waves arise from the most powerful and energetic processes in the universe. One such process is the collision of neutron stars. As two neutron stars orbit each other, they gradually lose energy by emitting gravitational waves, causing them to spiral closer until they eventually collide. At the moment of collision, a colossal amount of energy is released, generating powerful waves that propagate through the fabric of spacetime. The first direct detection of gravitational waves resulting from a neutron star collision occurred in August 2017, thanks to the LIGO and Virgo observatories. This event, designated GW170817, was a true breakthrough in astrophysics. It not only confirmed the existence of gravitational waves, but also opened up a new way of observing the universe. The collision of two neutron stars was also detected across various ranges of electromagnetic radiation, including gamma rays, X-rays, and visible light. This simultaneous observation across different wavebands marked the beginning of the era of multi-messenger astronomy, allowing scientists to study the same cosmic event using different channels of information. The detection of gravitational wave GW170817 provided invaluable insights into the nature of neutron stars and the extreme conditions in which they exist. The gravitational waves from the collision carried information about the masses and radii of the neutron stars, offering clues about the properties of the dense matter within them. Electromagnetic observations revealed the aftermath of the collision, including the formation of heavy elements such as gold and platinum, which are forged in the intense environment of merging neutron stars. The immense gravitational fields near neutron stars cause significant space-time curvature. This curvature is a key aspect of Albert Einstein's general theory of relativity, which describes gravity not as a force, but as a deformation of spacetime caused by mass and energy. Near a neutron star, this curvature reaches extreme values, and its manifestations can be observed in various ways. For example, light passing near a neutron star bends under the influence of its gravity, an effect known as gravitational lensing. This curvature can make a neutron star appear deformed or magnified when observed from Earth. Another consequence of extreme gravity near neutron stars is the slowing down of time. According to general relativity, time flows slower in regions with stronger gravitational fields. This means that for an observer near a neutron star, time will pass slower compared to an observer farther away. This effect, predicted by Einstein, is not noticeable in everyday life but becomes significant near massive objects like neutron stars. Neutron stars also serve as natural laboratories for testing Einstein's predictions about the behavior of matter and energy under extreme conditions. Precise timing measurements of pulsars, a type of rotating neutron star, allow scientists to test the effects of general relativity with high accuracy. For example, a binary pulsar system where two neutron stars orbit each other has provided some of the most stringent confirmations of general relativity to date. Observations of this system have confirmed several predictions of the theory, including the emission of gravitational waves and subsequent orbital decay. The study of neutron stars and their gravitational effects has expanded our understanding of general relativity and its significance for the universe. By observing these objects, scientists have been able to confirm many of Einstein's predictions and explore the limits of his theory. The extreme conditions near neutron stars push the boundaries of our knowledge, allowing for a deeper understanding of the nature of gravity and the fundamental laws of physics. The study of neutron stars opens a window into some of the most exotic states of matter in the universe. The extreme conditions within these stars lead to the formation of matter unlike anything found on Earth. From the dense core to the outer crust, neutron stars exhibit unique and unusual states of matter that challenge our understanding of physics. Deep within the core of a neutron star, where pressure and density reach maximum values, scientists hypothesize the existence of a state of matter known as quark-gluon plasma. Under normal conditions, protons and neutrons are composed of quarks held together by particles called gluons. However, the extreme conditions in a neutron star's core can break down these protons and neutrons into their constituent quarks and gluons, creating a soup-like mixture. This quark-gluon plasma is believed to resemble the conditions that existed immediately after the Big Bang, offering a glimpse into the early universe. The idea of quark-gluon plasma is supported by theoretical physics and experiments conducted at particle accelerators like the Large Hadron Collider. These experiments recreate the high-energy conditions necessary to form quark-gluon plasma on very small scales. Studying neutron stars provides an opportunity to observe this state of matter on much larger scales, offering valuable insights into the behavior of matter under extreme conditions. Other fascinating hypotheses are hidden within neutron stars, one of which concerns the existence of so-called strange matter. This exotic substance is composed of strange quarks, which differ from the ordinary up and down quarks that make up familiar matter by having greater mass. Under the colossal pressure prevailing in a neutron star's core, ordinary quarks can transform into strange ones, forming a new, potentially more stable form of matter. Surprisingly, this strange matter could be even denser than the incredibly dense neutronium that makes up the neutron star's core. The very idea of strange matter excites scientists, as it suggests the possibility of entire stars composed entirely of this exotic material. Such hypothetical objects are called strange stars. Although direct evidence for strange matter has not yet been found, the study of neutron stars offers promising prospects for testing this bold hypothesis. If strange matter truly exists, it could fundamentally alter our understanding of the fundamental forces and particles that make up the universe. Moving from the neutron star's core to its crust, we encounter another peculiar state of matter known as nuclear pasta. The neutron star's crust is subjected to colossal gravitational forces that compress atomic nuclei, giving them unusual shapes and structures. This results in matter with textures resembling various types of pasta, such as lasagna, spaghetti, and gnocchi. These bizarre shapes arise when nuclei align themselves in layers, tubes, and other complex configurations, seeking to minimize energy in this extremely dense environment. Nuclear pasta is not just a whimsical name. It's a unique phase of matter that challenges current understandings of nuclear physics. Studying nuclear pasta can shed light on the behavior of matter under extreme pressure and density, conditions virtually impossible to recreate in terrestrial laboratories. The unusual properties of nuclear pasta, such as its high strength and how it conducts heat and electricity, influence the thermal and magnetic characteristics of neutron stars. The existence of nuclear pasta was initially predicted by theoretical models, and recent computer simulations have provided a more detailed understanding of its structure and behavior. Observations of neutron stars, particularly the analysis of their thermal emission and magnetic fields, may confirm the presence of nuclear pasta and deepen our understanding of its unique properties. Neutron stars and black holes represent two extraordinary outcomes of stellar evolution, serving as different endpoints in the life cycle of massive stars. These objects, though born from similar processes, exhibit vastly different characteristics and behaviors, making them fascinating subjects of study in astrophysics. Neutron stars and black holes form from the remnants of massive stars that have exhausted their nuclear fuel. When a star significantly more massive than our Sun runs out of fuel, it can no longer resist the overwhelming force of gravity. The star's core rapidly collapses under its own weight, leading to a powerful supernova explosion. For stars with masses not exceeding approximately 20 solar masses, this collapse results in the formation of a neutron star. However, if the original star is even more massive, the core continues to compress, entering an even denser state and forming a black hole. During the formation of a neutron star, protons and electrons are compressed to form neutrons, leading to the creation of an incredibly dense object. Black holes, in contrast, arise when gravitational collapse continues unimpeded, compressing matter to a point of infinite density known as a singularity. The region around the singularity from which even light cannot escape is called the event horizon. This is a key distinction between neutron stars and black holes. While neutron stars remain tangible, albeit incredibly dense, objects, black holes represent a singularity where the familiar laws of physics break down and space-time is infinitely warped. Celestial bodies of colossal density, neutron stars and black holes, represent two extreme manifestations of gravity in the universe. The power of their gravitational pull is incredible, yet it manifests in different ways. Neutron stars, despite their monstrous degree of compression, possess a surface where gravity surpasses Earth's by billions of times. Imagine this situation. An object dropped from a height of just 1 meter above the surface of such a star would reach it at a speed of up to 2,000 kilometers per second. Nevertheless, theoretically, overcoming a neutron star's gravitational field is possible, provided sufficient energy is applied. In contrast, black holes are gravitational traps of such strength that nothing, not even light, can escape beyond the so-called event horizon. The speed required to overcome gravity at the event horizon exceeds the speed of light, making black holes fundamentally invisible. They can only be detected by their interaction with surrounding matter. The colossal gravity of these objects distorts spacetime to such an extent that the very flow of time near a black hole undergoes changes, as predicted by Albert Einstein's general theory of relativity. Observing and distinguishing between neutron stars and black holes relies on understanding the unique characteristics of each object. Neutron stars, especially pulsars, are detected by their regular pulses of radiation. These pulses arise from the rotation of the neutron star, which, like a lighthouse, sweeps beams of radiation across cosmic space. X-ray telescopes can detect high-energy radiation emanating from neutron stars, particularly those in binary systems. In such systems, the neutron star pulls matter from a companion star, heating it to extreme temperatures, which leads to the emission of X-rays. Black holes, by their mere nature, cannot be seen directly. Their presence is detected by their gravitational effect on nearby objects and their influence on surrounding matter. In a binary system, a black hole can pull matter from a companion star, forming an accretion disk. Friction and compression of matter as it approaches the black hole cause the emission of intense X-ray radiation, which is detected by space telescopes. Additionally, black holes can be identified by the characteristic motion of stars orbiting an invisible massive object. An example of this is the supermassive black hole known as Sagittarius A, located at the center of our galaxy. Gravitational waves are another powerful tool for studying both neutron stars and black holes. Collisions between neutron stars or black holes generate ripples in the fabric of spacetime that can be detected by observatories like LIGO and Virgo. The first detection of gravitational waves resulting from the merger of neutron stars, which occurred in 2017, confirmed many theoretical predictions about these objects and ushered in a new era in astrophysics. Similarly, the detection of gravitational waves from merging black holes has provided valuable insights into their properties and the nature of gravity itself. The comparative study of neutron stars and black holes helps scientists gain a deeper understanding of the laws of physics and the stages of stellar life cycles. Both types of objects challenge current understandings of matter, energy, and the fundamental forces that govern the universe. Neutron stars, with their superdense cores and powerful magnetic fields, allow for the investigation of matter's behavior at nuclear densities. Black holes, with their event horizons and singularities, push the boundaries of knowledge about gravity and spacetime. Neutron stars put on a captivating cosmic show, emitting energy across the entire electromagnetic spectrum, from radio waves to gamma rays. Among these emissions, X-rays hold particular significance. Observations made with powerful X-ray telescopes such as Chandra and Newton have provided invaluable information about the nature and behavior of neutron stars, revealing their mysteries in exquisite detail. The Chandra X-ray Observatory, launched by the National Aeronautics and Space Administration in 1999, is one of the most sophisticated X-ray telescopes ever built. It possesses a unique ability to detect and image X-ray emissions from high-energy regions of the universe, such as supernova remnants and the vicinity of neutron stars. Chandra's superb resolution has allowed astronomers to study the structure of neutron stars and their surroundings in detail, gaining important insights into their formation and evolution. Newton, a European Space Agency mission, complements Chandra's capabilities with its suite of powerful X-ray instruments. Since its launch in 1999, Newton has provided a vast amount of data on neutron stars, helping scientists understand the intense and dynamic processes occurring within these celestial bodies. The collaborative work of these two telescopes has revolutionized our understanding of neutron stars, revealing the complexity and splendor of these astonishing objects. The X-ray emission from neutron stars displays a remarkable diversity. In the case of isolated neutron stars, X-rays often originate from a hot surface, heated either by residual heat from the star's formation or by magnetic and accretion processes. In binary systems, where a neutron star pulls matter from its companion, the infalling material heats up to millions of degrees, producing bright X-ray emission. These emissions carry invaluable information about the physical conditions and processes occurring within and around neutron stars. One of the most important methods for studying neutron stars is spectroscopy, which is the analysis of light emitted by these celestial bodies. By examining the spectrum of X-rays and other types of radiation coming from a neutron star, astronomers can determine its composition, temperature, density, and magnetic field strength. Neutron star spectroscopy involves breaking down light into its constituent wavelengths and identifying unique spectral lines, a kind of fingerprint of various elements and ions. Spectroscopic studies have shown that neutron stars possess atmospheres composed primarily of hydrogen and helium, with minor traces of heavier elements. The spectral lines observed in the X-ray range allow for precise measurements of surface temperature and gravitational redshift, enabling scientists to investigate the star's powerful gravitational field. These observations help build a detailed picture of the neutron star's surface and internal structure. Neutron star mergers, when two neutron stars collide and merge, are among the most energetic and spectacular events in the universe. These collisions give rise to a phenomenon known as a kilonova, a transient astronomical event that emits bright light across the entire electromagnetic spectrum. Kilonovae result from the radioactive decay of heavy elements formed during the merger process, accompanied by the release of a colossal amount of energy and light. The visual representation of a kilonova is a rare and breathtaking sight. As two neutron stars spiral closer and collide, they generate a burst of gravitational waves, followed by a flash of gamma rays. As the ejected material from the collision expands and cools, it begins to emit light across the entire spectrum, from ultraviolet to infrared. This light show can last from a few days to several weeks, gradually fading as the radioactive elements decay. The kilonova observed after the event designated GW1708-17 in 2017 was the first such phenomenon recorded by scientists. Gravitational waves from this neutron star merger were detected by the LIGO and Virgo observatories, and within hours, telescopes worldwide were pointed at the source of the signal. The data obtained allowed for a detailed study of the kilonova, revealing the formation of heavy elements such as gold and platinum. This discovery confirmed the hypothesis that neutron star mergers are a primary source of these elements in the universe. Kilonovae are not only spectacular visual events, but also provide valuable scientific data. By studying the light curves and spectra of kilonovae, astronomers can gain information about the physical processes occurring during neutron star mergers, the properties of the ejected material, and the mechanisms of heavy element formation. These events also help refine models of neutron star internal structure and the behavior of matter under extreme conditions. Neutron stars are not just amazing remnants of massive stars, but also key participants in spectacular events known as supernovae. These stellar explosions are among the most powerful phenomena in the universe, and the formation of a neutron star is inextricably linked to the dynamics of these colossal outbursts. When a massive star exhausts its nuclear fuel, it loses the ability to resist gravitational compression. This leads to a catastrophic collapse of the star's core, followed by a rebound that generates shock waves propagating outward, causing the explosion of the star's outer layers as a supernova. During this process, the star's core compresses to incredible density, leading to the formation of a neutron star. The presence of a neutron star at the very center fundamentally influences the mechanics of a supernova explosion. The powerful gravitational collapse and subsequent formation of a neutron star lead to the release of a colossal amount of energy. This energy initiates the supernova explosion, ejecting the star's outer layers into space at incredible speeds. The shock waves generated by this explosion propagate, heating the surrounding interstellar medium and stimulating the formation of new stars. This process injects heavy elements formed during the star's lifetime and at the moment of the explosion into the galaxy, enriching it with building blocks for future generations of stars and planets. The remnants of these supernova explosions, including both the expanding shell of gas and the newly formed neutron star, significantly impact their surrounding space. Shock waves from the explosion compress nearby clouds of gas and dust, potentially triggering the birth of new stars. Additionally, these shock waves disperse heavy elements such as iron, calcium, and nickel throughout the galaxy, contributing to its chemical evolution. Even after the initial supernova explosion subsides, neutron star remnants continue to influence their surroundings for extended periods. The intense radiation and stellar winds from young neutron stars can energize the surrounding material, creating complex and captivating structures known as supernova remnants. These remnants, observable across the electromagnetic spectrum, are a mixture of expanding gas, shock waves, and radiation, often displaying intricate filaments and loops. Comparing supernova remnants and neutron star remnants provides valuable insights into the aftermath of stellar explosions. Supernova remnants are larger structures formed by the explosions, shock waves, and ejected material. These remnants can extend for tens of light years and are often observed in visible light, X-rays, and radio waves. Studying supernova remnants helps astronomers understand the energetics and dynamics of the explosion, the distribution of heavy elements, and interactions with the interstellar medium. On the other hand, neutron star remnants are the compact cores left behind after the explosion. These remnants, especially pulsars, emit radiation across the entire electromagnetic spectrum, providing clues to understanding the properties and behavior of neutron stars. Observations of neutron star remnants allow scientists to investigate the extreme conditions existing within neutron stars, such as their powerful magnetic fields and rapid rotation. The combined study of both the extensive supernova remnants and the compact neutron star remnants offers a comprehensive view of the life cycle of massive stars and their impact on the galaxy. The role of neutron stars in supernovae, also extends to their contribution to cosmic phenomena such as gamma-ray bursts. These bursts, which are the most energetic events in the universe, are generally believed to be associated with certain types of supernovae, especially those involving the collapse of massive stars into black holes or neutron stars. Studying gamma-ray bursts associated with supernovae provides additional insights into the extreme conditions and processes that occur during these catastrophic events. The impact of neutron star remnants on the evolution of the galaxy cannot be overstated. By injecting energy and heavy elements into the interstellar medium, they contribute to the formation of galactic structure and composition. Shock waves from supernovae can trigger the formation of new stars, influencing the birth and evolution of stars and planetary systems. Radiation and stellar winds from neutron stars continue to affect the surrounding environment, contributing to the dynamic and ever-changing nature of the galaxy. In essence, neutron stars, born from the ashes of massive stars and supernova explosions, are both remnants and architects of cosmic evolution. The study of neutron stars has a rich history, marked by groundbreaking discoveries and evolving theories that have deepened our understanding of these enigmatic objects. One of the most significant events on this journey was the discovery of pulsars by Jocelyn Bell Burnell, which ushered in a new era in astrophysics and laid the groundwork for decades of research and discoveries. In the annals of astrophysics, there's a captivating chapter dedicated to neutron stars, full of unexpected findings and discoveries that have revolutionized our understanding of the cosmos. In 1967, Jocelyn Bell Burnell, then a graduate student at Cambridge University, working with her supervisor Anthony Hewish, was using a new type of radio telescope designed to study quasars. During observations, Bell Burnell noticed a series of regular repeating signals, which she initially dismissed as interference. These signals, sharp pulses of radio waves, were unlike anything previously observed. After meticulous analysis and ruling out various terrestrial sources of interference, Bell Burnell and her team concluded they were of cosmic origin. This discovery, initially dubbed LGM-1 for Little Green Men, was later identified as radiation from a rapidly rotating neutron star. These pulsars, as they were subsequently named, emit beams of radiation from their magnetic poles. As the neutron star rotates, it sweeps these beams across cosmic space, creating the effect of pulsating signals observed from Earth. The discovery of pulsars not only confirmed the existence of neutron stars, but also provided a powerful tool for studying these exotic objects and testing fundamental laws of physics under extreme conditions. Jocelyn Bell Burnell's discovery was a turning point in astrophysics. It vividly demonstrated that neutron stars, which had existed only in theory since the 1930s, were real objects accessible for observation and study. This discovery sparked a surge of interest and research aimed at exploring neutron stars and their unique properties. It also paved the way for the detection of numerous other pulsars, each providing valuable insights into the behavior of matter in colossal gravitational and magnetic fields. As our knowledge of neutron stars deepened, so did theoretical understandings of them. Initially, neutron stars were conceived as relatively simple objects, composed primarily of neutrons. However, with the discovery and study of an increasing number of pulsars, it became evident that neutron stars possessed a much more complex structure. The understanding that neutron stars could have incredibly powerful magnetic fields led to the discovery of magnetars, marking a significant step in theoretical development. These magnetic fields, millions of times stronger than Earth's, profoundly influence neutron star radiation and their interaction with the surrounding environment. The study of neutron stars also received a powerful boost from advancements in technology and observational methods. The launch of powerful space telescopes such as the Hubble Space Telescope, the Chandra X-ray Observatory, and XMM Newton allowed astronomers to observe neutron stars with unprecedented detail and across various ranges of the electromagnetic spectrum. These observations revealed complex structures and behavioral features of neutron stars, from their scorching surfaces to the dynamic processes occurring in their magnetospheres. Significant milestones in neutron star research have profoundly impacted astrophysics. The detection of gravitational waves from merging neutron stars, such as the GW170817 event in 2017, was a true breakthrough. This discovery, made by the LIGO and Virgo observatories, confirmed that neutron star collisions are a powerful source of gravitational waves and provided a new way to study these cosmic cataclysms. Multi-messenger observations of GW170817, encompassing electromagnetic signals across the spectrum, provided a comprehensive view of the merger process and its aftermath. Another important milestone was the discovery of the first millisecond pulsar in 1982. These pulsars, spinning hundreds of times per second, are among the fastest rotating neutron stars known to science. The study of millisecond pulsars has provided valuable information about the evolution of neutron star rotation and the mechanisms that can accelerate them to such incredible speeds. These discoveries also highlighted the important role of neutron stars in binary systems and the complex interactions that can occur under such conditions. The evolution of our understanding of neutron stars is marked by a constellation of outstanding discoveries, each building upon previous achievements, expanding the horizons of knowledge about these captivating cosmic objects. From the initial theoretical constructs of Fritz Zwicky and Walter Baade, to the groundbreaking observations of Jocelyn Bell Burnell and the detailed investigations carried out by modern telescopes, the path of knowledge has been marked by relentless progress and breakthrough discoveries. Neutron stars not only challenge modern scientific understanding, but also stimulate profound philosophical inquiries. They exist in a realm where the familiar laws of physics become distorted and at times cease to apply altogether, serving as a vivid reminder of the universe's complexity and boundlessness. Contemplating these dense remnants of stellar explosions gives rise to deep existential questions about humanity's place in the cosmos and the nature of reality itself. The very existence of neutron stars, with their unimaginable density and powerful magnetic fields, underscores the diversity and often brutal nature of the processes that shape the universe. These objects serve as a vivid reminder that the universe is by no means a static and tranquil place, but a dynamic and at times chaotic environment. The forces at play within and around neutron stars are so colossal as to be almost incomprehensible, offering a humbling perspective on our own existence. Reflecting on the implications of neutron stars, one confronts the immense scales of time and space. Neutron stars can exist for billions of years, vastly outliving the explosions that created them. They persist in a state of exceptional stability and immutability, a stark contrast to the fleeting nature of human life. This contrast can lead to contemplation on the nature of being and the transient character of personal experience compared to the grand temporal scales of the cosmos. Neutron stars also illustrate the concept of extremes in the universe. Their very existence challenges the understanding of matter and energy, demonstrating that the universe is capable of creating conditions far exceeding those we encounter on Earth. These extreme manifestations push the boundaries of knowledge and force a re-evaluation of what is possible. They serve as a reminder that everyday experience represents only a small fraction of what the universe has to offer. Reflections on neutron stars can lead to an awareness of humanity's significance in the grand scheme of the cosmos. Our planet is but a tiny speck of dust, and humanity's existence a brief moment in cosmic time. Neutron stars, with their incredible density and powerful gravitational fields, exist in a state almost entirely alien to our understanding. This realization can be both humbling and awe-inspiring, highlighting humanity's small place in the universe, but also its capacity for knowledge and discovery. The study of neutron stars and astrophysics in general contributes to the formation of a cosmic worldview that can have a profound impact on human philosophy. By gazing at the universe and observing objects like neutron stars, we gain a deeper understanding of the complexity and beauty of the cosmos. This perspective stimulates a sense of wonder and curiosity, prompting us to seek answers to fundamental questions about our origin and place in the universe. Moreover, the scientific endeavors aimed at comprehending neutron stars reflect a profound human trait, an insatiable thirst for knowledge. Despite the challenges and often unfathomable scales, humanity continues to push the boundaries of understanding. This pursuit is a testament to the power of the human spirit and an innate desire to explore and comprehend the world around us. It underscores the importance of scientific research as a means of expanding horizons and deepening our understanding of the universe. The mania of the universe. Reflecting on the nature of neutron stars inevitably leads one to ponder the profound interconnectedness of all elements in the universe. It is within the hearts of stars that the very elements comprising our bodies and our planet are forged. Dispersed throughout the galaxy by supernova explosions, these elements become part of everything that exists. In the most literal sense, each of us is made of stardust. This realization fosters a sense of unity and interconnectedness with the cosmos, reminding us that we are an integral part of a grand cosmic story. Observing neutron stars and contemplating their unique properties also influences our perception of life's fragility and value. The extreme conditions prevailing within and around these cosmic objects are utterly incompatible with life as we know it. This vividly demonstrates the delicate balance required to sustain life. Such an awareness allows for a renewed perspective on the uniqueness of our planet and underscores the importance of protecting the fragile ecosystems that enable life to exist. Collisions of neutron stars and black holes represent some of the most spectacular and energetically powerful phenomena in the universe. Each such collision generates unique gravitational wave signals that carry valuable information about the nature of these cosmic objects. Studying these collisions not only helps us understand the properties of neutron stars and black holes more deeply, but also opens new horizons in the investigation of processes that govern cosmic evolution and the formation of various structures. Gravitational wave signals generated by neutron star collisions differ significantly from signals produced by black hole collisions. When two neutron stars spiral closer and eventually merge, the gravitational waves generated contain a wealth of detail reflecting the complex interaction processes of these ultra-dense objects. The waveform produced by neutron star mergers is characterized by several features, including an inspiral phase, where the stars orbit each other with increasing speed, and the merger phase itself, when the two stars collide and coalesce. The resulting gravitational wave signal is typically longer and more complex compared to signals arising from black hole mergers. Highly sensitive observatories like LIGO and Virgo are used to detect these gravitational waves. These instruments can measure minute distortions in spacetime caused by passing gravitational waves. Signals from neutron star mergers can be identified by their frequency and amplitude characteristics, which allow for the determination of the masses and radii of the colliding stars. The detection of gravitational waves from neutron star mergers has provided irrefutable evidence for the existence of these ultra-dense objects and has enabled scientists to investigate their internal structure and composition. In contrast, gravitational wave signals arising from black hole collisions are typically simpler and shorter in duration. When two black holes merge, they emit gravitational waves primarily in the final moments of inspiral and merger, followed by a brief ring-down phase as the newly formed black hole settles into a stable state. These signals are generally characterized by higher frequencies and larger amplitudes compared to neutron star merger signals due to the more massive and compact nature of black holes. The outcomes of these collisions also differ significantly. The merger of two neutron stars can result in the formation of a hypermassive neutron star, which exists for a short time before collapsing into a black hole. This transient object can emit powerful electromagnetic radiation, including gamma-ray bursts and colonovae, as debris from the collision heats up and is ejected into space. These emissions provide additional data that complement gravitational wave observations, allowing for a more complete understanding of the merger process. Black hole mergers, on the other hand, result in the formation of a single larger black hole. These events are typically not accompanied by significant electromagnetic emissions, making them observable primarily through gravitational waves. The ring-down phase of the newly formed black hole generates a characteristic gravitational wave signal that helps determine the properties of the final black hole, such as its mass and spin. The mass and spin of these celestial bodies play a key role in their behavior and interaction with the environment. Collisions between neutron stars and black holes are of immense importance for cosmic evolution and the formation of large-scale structures in the universe. Neutron star mergers, which produce heavy elements such as gold and platinum, enrich the galaxy with chemical elements. These elements are dispersed into interstellar space and can subsequently become part of new stars and planets. The detection of so-called kilinovae, which arise from neutron star mergers, serves as direct evidence of this nucleosynthesis process, underscoring the importance of such events in the cosmic cycle of matter. Black hole mergers, while not directly leading to chemical enrichment, influence the dynamics and evolution of galaxies. The coalescence of black holes can lead to the growth of supermassive black holes at the centers of galaxies, which, in turn, play a crucial role in regulating star formation processes and shaping the overall structure of galaxies. The energy and momentum released as gravitational waves during black hole mergers can also affect the distribution of matter in the surrounding regions, impacting the processes of galaxy formation and evolution. The extreme conditions found in neutron stars, such as colossal gravity, incredible density, and powerful magnetic fields, provide unique opportunities to study and potentially confirm theories beyond the standard model of physics. These investigations aim to deepen our understanding of the universe and bring us closer to a unified theory of everything. Quantum gravity represents one of the most challenging problems in modern physics. This field of science aims to unite the principles of quantum mechanics, which describe the behavior of particles at the microscopic level, with general relativity, which describes gravitational interaction on the scale of the universe. Neutron stars, with their intense gravitational fields and superdense matter, are an ideal testing ground for theories of quantum gravity. The extreme conditions within and around neutron stars push the boundaries of our understanding and may hold the key to unraveling the nature of gravity at the quantum level. Observations of neutron stars, particularly through gravitational wave astronomy, can provide indirect evidence of gravity's behavior under extreme conditions. For example, precise measurements of neutron star collisions by observatories like LIGO and Virgo can help test predictions made within quantum gravity theories. These observations may reveal deviations from general relativity's predictions, indicating the existence of new physics and offering insights into how gravity operates at the quantum level. String theory represents another hypothetical concept striving to unify all fundamental forces and particles into a single theory. According to string theory, the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. These strings can exist in multiple dimensions, and their vibrations determine the properties of particles and forces. Neutron stars, with their extreme conditions, may provide a context in which some predictions of string theory can be tested or observed. One intriguing idea in string theory is the concept of extra dimensions. Neutron stars, with their high density and strong gravitational fields, could influence or be affected by these extra dimensions, which might be observable. For example, the behavior of matter and radiation near a neutron star could reveal subtle effects indicating the existence of extra dimensions. While direct evidence for string theory has not yet been found, neutron stars offer a natural laboratory for exploring these possibilities. Beyond string theory, other speculative ideas related to neutron stars exist. These include concepts such as loop quantum gravity, which suggests that space-time itself has a discrete structure at the smallest scales, as well as various models predicting the existence of exotic particles or forces. Neutron stars, with their unique conditions, provide a testing ground for these theories, potentially revealing new aspects of the universe that cannot be observed elsewhere. The quest for a unified theory of everything, capable of combining all fundamental forces of nature within a single conceptual framework, is rightly considered one of the most ambitious tasks of modern physics. In this context, neutron stars play an exceptional role, providing a unique opportunity to test and calibrate theories aimed at achieving this long-awaited unification. The extreme conditions prevailing deep within neutron stars form a kind of bridge between the microscopic quantum world and the macroscopic world of gravity, allowing scientists to investigate the complex interactions between these realms. Efforts to unify fundamental forces involve a deep understanding of how the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity can be described by a single theoretical model. Neutron stars, composed primarily of neutrons held together by the strong nuclear force and subjected to colossal gravitational fields, become ideal objects for studying these interactions. By observing and modeling the behavior of matter in neutron stars, scientists hope to gain valuable insights into how these forces can be unified within a single theory. One of the key ways neutron stars contribute to unification efforts is by studying their internal structure. The density of matter inside a neutron star reaches such incredible values that matter can exist in a state combining aspects of both nuclear and gravitational physics. By understanding the equation of state, which describes the behavior of matter at such extreme densities, researchers can test the predictions of various unification theories. Observations of neutron star properties, such as their mass and radius, provide critically important data for these studies. Another important contribution to the study of fundamental forces is the investigation of neutron star mergers and the resulting gravitational waves. These cosmic events carry a wealth of information about the behavior of matter under extreme conditions and the nature of gravity itself. Precise measurements of gravitational waves emanating from neutron star mergers can help test various models of gravity and place constraints on theories seeking to unify fundamental forces. Neutron stars, with their incredible power and unique conditions, serve as natural laboratories for exploring the most fundamental questions of physics. Studying these amazing objects paves the way for understanding the deepest mysteries of the universe and the forces that govern it. Neutron star jets and quasar jets represent some of the most energetic and captivating phenomena in the universe. Both of these phenomena involve the ejection of matter at relativistic speeds, meaning speeds close to the speed of light. Despite certain similarities, these jets differ in their formation mechanisms, radiation characteristics, and impact on the surrounding environment, providing unique insights into the diverse processes occurring in space. Relativistic jets are powerful streams of charged particles that are ejected from the vicinity of compact astrophysical objects. Neutron star jets are typically associated with pulsars or neutron stars in binary systems where matter from a companion star flows onto the neutron star's magnetic poles. This matter is then accelerated along magnetic field lines and ejected at speeds close to the speed of light. These jets are often observed in X-ray binary systems, where the interaction between the neutron star and its companion generates high-energy radiation. Quasar jets, in turn, originate from regions surrounding supermassive black holes located at the centers of active galaxies. As matter accretes onto the black hole, it forms an accretion disk that heats up and emits a colossal amount of energy. Some of this material is ejected along the black hole's rotation axis, forming jets that extend for thousands of light years into space. The precise mechanisms governing these jets involve complex interactions between the black hole's magnetic field, accreting matter, and relativistic effects. In the cosmic expanse of the universe, jets, powerful ejections of energy and matter emanating from the vicinity of compact objects like neutron stars and quasars, present a captivating spectacle. These cosmic streams, propelled at immense speeds, serve as natural laboratories for investigating extreme physical phenomena and relativistic effects. The speeds of these jets reach relativistic values, but quasar jets, thanks to colossal gravitational forces, can achieve even higher velocities. Neutron star jets are generally less powerful, but can still accelerate particles to a significant fraction of the speed of light. Such high speeds lead to relativistic effects, such as time dilation and the Doppler shift of emitted light, which are crucial for understanding the physical conditions prevailing within the jets. The radiation characteristics of neutron star jets and quasar jets also show significant differences. Neutron star jets emit radiation across the entire electromagnetic spectrum with a pronounced presence in the X-ray and radio bands. The spectral signatures of these jets reveal information about the accelerated particles, magnetic field strength, and the interaction of the jets with surrounding matter. Observations of neutron star jets can uncover periodic variations related to the neutron star's rotation and its orbital motion in binary systems. Quasar jets, in contrast, are powerful sources of radio waves and often show strong emission in the optical, ultraviolet, and even gamma-ray bands of the spectrum. The spectral energy distribution of quasar jets provides insights into the physical processes occurring near the supermassive black hole, such as synchrotron radiation from high-energy electrons spiraling in magnetic fields, and inverse Compton scattering, where low-energy photons gain energy through interaction with relativistic electrons. The variability of quasar jets, including rapid changes in brightness and spectral characteristics, reflects the dynamic environment near the black hole. The impact of these jets on the surrounding environment is significant, but differs for neutron stars and quasars. Neutron star jets, despite their power, have a more localized effect. They can heat and ionize matter in their immediate vicinity, creating shock waves and accelerating cosmic rays. These interactions manifest as bright X-ray and radio sources, providing information about the density and composition of the surrounding interstellar medium. Quasar jets, due to their immense power and scale, can influence entire galaxies. They transport energy and momentum over colossal distances, affecting star formation and gas distribution in the host galaxy. Jets can shape large-scale structures known as radiolobes, where ejected material interacts with the intergalactic medium. These interactions lead to the formation of hot spots and shock fronts, which are observed as extended radio sources. Feedback from quasar jets can regulate the growth of the supermassive black hole and the evolution of the galaxy, playing a crucial role in the cosmic ecosystem. The study of these jets through observations across the electromagnetic spectrum provides important insights into the processes underlying high-energy astrophysical phenomena. Advanced telescopes such as the Chandra X-ray Observatory, the Hubble Space Telescope, and the Very Large Array have enabled detailed observations of neutron star and quasar jets, revealing their structure, dynamics, and impact. Comparing neutron star jets and quasar jets highlights the diversity of astrophysical processes occurring in the universe. Neutron stars have become intriguing candidates in the search for understanding one of the universe's most profound mysteries: dark matter. Dark matter is an invisible substance that makes up about 27% of the universe, which neither emits, absorbs, nor reflects light, making it incredibly difficult to detect directly. Its presence is inferred from its gravitational effects on visible matter, such as the rotation of galaxies and the bending of light from distant stars. In the boundless expanse of space, amidst the shimmering distant stars, neutron stars, with their incredible density and powerful gravitational fields, present a unique laboratory for studying and possibly detecting dark matter. One of the key questions occupying researchers in this field is the ability of neutron stars to capture particles of this mysterious substance. As they move through the galaxy, dark matter particles can gravitationally interact with neutron stars. Thanks to the colossal gravitational pull of these stars, dark matter particles can be captured and drawn into their inner layers. Theoretical calculations show that over time, neutron stars can accumulate a significant amount of dark matter in their cores. The potential capture of dark matter particles by neutron stars could have several important consequences. One of the primary effects is an influence on the star's thermal evolution. If dark matter particles interact with ordinary matter, they can transfer energy within the neutron star, thereby altering its temperature and cooling rate. This energy transfer could lead to noticeable changes in the thermal emission of neutron stars, providing indirect evidence of dark matter interactions. Another consequence of dark matter accumulation in neutron stars is its possible impact on their structure and stability. Dark matter particles could form a dense core within the neutron star, influencing its overall mass and radius. Depending on the characteristics of the dark matter particles, this could lead to changes in the observed parameters of the star, such as its rotation rate and magnetic field strength. These changes could be detected through high-precision measurements of pulsars, rapidly rotating neutron stars that emit regular pulses of radiation. Of particular interest is the possibility of the formation of a Bose-Einstein condensate of dark matter particles inside a neutron star. This exotic state of matter, where particles occupy the same quantum state, could possess unique properties and influence the neutron star's behavior. For example, the presence of a dark matter condensate could lead to new types of oscillations or instabilities within the star, potentially generating detectable signals in the form of gravitational waves or changes in the star's rotation period. The study of dark matter interactions with neutron stars is in its early stages, but holds immense potential for expanding our knowledge of both dark matter and neutron star physics. Observational studies aimed at detecting signs of dark matter in neutron stars include searching for anomalies in their thermal emission, rotational behavior, and gravitational wave signatures. These observations require the use of highly sensitive instruments and long-term monitoring to identify subtle effects that could indicate the presence of dark matter. In addition to observational methods, theoretical research plays a vital role in studying potential interactions between dark matter and neutron stars. Computer modeling and simulations help predict the behavior of dark matter particles in the extreme environment of a neutron star. These models can guide observational strategies and aid in interpreting any detected anomalies. One actively studied area is the possibility of dark matter particle annihilation within neutron stars. If dark matter consists of particles capable of annihilating each other upon collision, this process could release a significant amount of energy. This energy could heat the neutron star, leading to noticeable changes in its thermal emission. Detecting such thermal effects would provide compelling evidence for the existence of dark matter and offer insights into its properties. The potential role of neutron stars in detecting and understanding dark matter is not limited to the study of individual objects. Neutron star mergers, which generate powerful gravitational waves and electromagnetic signals, can also provide valuable insights into the nature of dark matter. During the violent merger process, any dark matter present in the neutron stars is subjected to extreme conditions, potentially leading to unique characteristics in the emitted radiation and gravitational waves. The intersection of neutron star physics and dark matter research represents a frontier of modern astrophysics, capable of revealing fundamental truths about the universe. By studying neutron stars and their interaction with dark matter, scientists hope to make breakthroughs in understanding both these enigmatic objects and the elusive substance that shapes the cosmos. The quest to detect dark matter using neutron stars serves as a testament to the ingenuity and determination of researchers, driven by the desire to unravel the deepest mysteries of creation. The nature of time near neutron stars undergoes profound changes due to their extreme gravitational fields, opening unique perspectives in understanding the fundamental nature of time and space-time. Neutron stars, with their colossal density and intense gravitational forces, create conditions where the effects predicted by Albert Einstein's general theory of relativity become particularly pronounced. Studying these relativistic effects can shed light on the phenomenon of time dilation and the very structure of space-time. Albert Einstein's general theory of relativity describes gravity not merely as a force, but as a curvature of space-time caused by mass and energy. This curvature influences the passage of time. Stronger gravitational fields cause time to slow down relative to weaker ones. This phenomenon, known as gravitational time dilation, is especially noticeable near massive objects like neutron stars. In the immediate vicinity of a neutron star's surface, the gravitational field is so powerful that it warps spacetime to an unprecedented degree. For an observer at a safe distance, time appears to flow slower for anything near the neutron star. This means that if someone could survive near the surface of a neutron star, they would age slower compared to someone far away from it. Such extreme time dilation is a direct consequence of the intense gravity that characterizes these stellar remnants. To illustrate, one can imagine the concept of a gravitational well. Neutron stars create deep gravitational wells due to their mass and compactness. The deeper one descends into this well, the stronger the gravitational field and the more pronounced the time dilation. On the surface of a neutron star, this well is incredibly deep, leading to significant time dilation effects. Studying these effects near neutron stars provides valuable insights into the nature of time itself. Time dilation, predicted by the theory of relativity, has been confirmed by numerous experiments and observations. But neutron stars offer an extreme environment where these effects are amplified. By observing the behavior of time in such strong gravitational fields, scientists can test the limits of relativity theory and explore the interaction of time and gravity at the most fundamental levels. One practical way to study time dilation near neutron stars is through observations of pulsars. Pulsars are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. As these beams sweep past Earth, they create a regular pulsating signal that can be measured with high precision. Any deviations in the arrival time of these pulses can reveal the effects of gravitational time dilation and provide insights into the structure of spacetime around the neutron star. Neutron stars serve as a unique laboratory for testing Albert Einstein's general theory of relativity, providing an opportunity to study the effects of extreme gravity and time dilation under the harshest conditions known to modern science. For example, when a pulsar, a rapidly rotating neutron star, enters a binary system with another star, the gravitational interaction between these two cosmic bodies produces variations in the arrival times of the pulsar's pulses. By analyzing these variations, scientists can measure the effects of time dilation and investigate the geometry of spacetime in that system. Such observations have provided some of the most precise confirmations of general relativity, validating its predictions with astonishing accuracy. The extreme gravitational fields surrounding neutron stars also open opportunities to study the concept of spacetime curvature. According to general relativity, mass and energy curve spacetime, and this curvature influences the movement of objects and the passage of time. Near a neutron star, the curvature becomes so strong that it can significantly bend light, creating an effect known as gravitational lensing. By investigating how light and other forms of radiation are bent and distorted by a neutron star's gravity, scientists can map the curvature of spacetime and gain insights into the fundamental properties of gravity. Gravitational waves, which are ripples in the fabric of spacetime caused by accelerating massive objects, also provide a unique way to study the effects of extreme gravity in the vicinity of neutron stars. When merging, neutron stars generate powerful gravitational waves that can be detected by observatories like LIGO and Virgo. These waves carry information about the dynamics of the merger process and the properties of neutron stars, including the effects of time dilation and spacetime curvature. By analyzing gravitational wave signals, scientists can test the predictions of general relativity and investigate the behavior of spacetime under extreme conditions. The study of time near neutron stars not only expands our understanding of these amazing objects, but also deepens our overall comprehension of the universe. Time dilation and spacetime curvature are fundamental aspects of general relativity, and their study in the context of neutron stars provides crucial tests of this theory. These investigations help refine our models of gravity and improve our understanding of how the universe functions on the largest and smallest scales. Moreover, the knowledge gained from studying neutron stars can have far-reaching implications for our understanding of the cosmos. Neutron stars, with their frightening yet beautiful nature, stand as a symbol of the universe's grandeur and complexity. They capture our imagination and inspire us to go beyond the familiar, to explore the extreme states of matter and energy. By studying these remarkable objects, we come to a deeper understanding of the cosmos and our place within it. Further exploration of neutron stars promises to continue revealing the wonders of the universe, inviting us to marvel at the beauty and power that lie beyond our everyday experience. As we venture into this realm of extremes, we carry with us the awareness that the universe is boundless, dynamic, and full of wonders yet to be discovered. Friends, thank you for watching. See you in the next video.